Hello everyone, we will present our work of trading bot assignment. This is our group members of group 13. I'm Zhiwang. I will begin by giving a short overview of the optimization algorithms we explored in part 1 of our project. To build a robust Bitcoin trading bot, we needed algorithms that could handle complex, high-dimensional, and noisy search spaces, which are common challenges in financial trading. So we focused on 6 natural-inspired algorithms, each of which simulates a natural phenomenon, to explore the solution space. PSO, particle swarm optimization based on birds flocking behavior. ABC, artificial bean colony, mimics how bees search for food. BOA, butterfly optimization algorithms based on butterflies' use of scent trails. ALO, antline optimizer, models how antlions trap their prey. MBA, mind blast algorithm, inspired by the debris spread from an explosion. AT, artificial train algorithm, based on train growth and new trait follow. In addition to these 6, we also tested one algorithm during implementation, high climbing, a simple local search that makes great improvements. We can group them into broadened categories. PSO, ABC, and BOA emphasize social behavior and communication, where individuals learn from and interact with others in a swarm or colony. In contrast, AT and MBA simulate growth process or physical reactions, such as train brancher or explosions. ALO and BOA also incorporate adaptive mechanics that adjust the balance between exploration and exploitation dynamically during the search. PSO and ABC are more established and have been extensively validated across various application domains. By contrast, ALO and MBA are relatively new, both developed after 2010, and where they offer fresh perspectives, they still lack large-scale testing. Finally, AT and BOA are emerging algorithms. They show promise but have not yet been deeply explored. Each algorithm balances exploration and exploitation differently. PSO and BOA converge quickly, ideal for parameter turning like MA flatters. ABC is stable in noisy environments like volatile price state. ALO and MBA emphasize exploration and may suit more dynamic bots. In summary, this algorithm review helped us compare a wide variety of operators and select the most suitable one. Well, that's all I want to say for this part. I will hand it over to my teammates. Thanks for listening.
Hi, I'm Joel. I'm going to do an overview of the trading bot's design and parameters. First, I'll go over the bot design. This ultimately dictates how the bot decides the buy and sell actions for a given set of price data and parameters. Our trading bot is based on the double moving average crossover strategy. Since this strategy is detailed in the project description, I'll just give a brief overview over the steps to calculate this. Firstly, a simple moving average, a linear moving average, and an exponential moving average are combined with a weighted sum to make two weighted moving average signals, a long signal and a short signal. Then the difference is calculated between these two signals by subtracting one from the other. And then finally, the buy signal is then generated by iterating through the difference of the two signals and then placing a +1, a buy, when the difference changes from negative to positive, and a -1, a sell, whenever the difference changes from positive to negative. Now that we've looked at how the bot functions, we can look at its parameters. So for each of the weighted moving averages, there are 7 parameters. There are 3 parameters for the weights of each moving average, another 3 for the window lengths of each moving average, and then an extra parameter for the exponential moving average's alpha value. So the 3 weights are all real numbers between 0 and 1 and must all add to 1. There are multiple ways to enforce this constraint, but we did it by dividing all the weights by the sum of the weights. So if a bot with the parameters 1, 1, 1 is run, Each of the weights would be adjusted to 1/3 each. The window lengths are all integers between 1 and 200. We decided on 200 days as the maximum window length, since it's the maximum length typically used in trading strategies, and large window lengths start to rely on padded values from before the training data, which are inaccurate. And finally, the exponential moving average alpha parameter is also a real number between 0 and 1. These 7 parameters for each of the 2 signals gives us a total of 14 parameters in total. Now, as I mentioned before, there are multiple ways to enforce the constraint that the 3 weights add to 1. One way to do this is by parameterizing 2 of the weights and expressing the 3rd weight in terms of the other 2, as shown in the equation here. Doing this can reduce the total number of dimensions from 14 to 12, which would likely find better results faster as it reduces the size of the hypothesis space, whilst not compromising on the actual algorithms that can come out of it. However, we decided to stick with 14 parameters since the focus of the project was on the optimization algorithms, and so this was considered out of scope. Now that we can describe any potential bot with a set of 14 parameters, we're left with the question, how do we choose these parameters? This will be answered by my teammate as they talk about selecting an optimization algorithm. Thank you.
Hi, I'm Iran, and I'm gonna introduce our project section 3 algorithm selection. Picking up from Joe's board design section, our robot has 14 parameters, and these 14 parameters are continuous. The search space is rugged. Every time we test the parameter set, we need to replay years of Bitcoin prices. So you want the optimizer can search the whole space and also finish it quickly. So with that in mind, here's how we set our selection criteria. So we have 4 criteria here. The firstly, exploration. One can escape many local peaks. And secondly, we only want just have few meta parameters. And thirdly, we hope it can support natively for real values. And finally, because we will only be graded in 1 or 2 seeds, so we want it to have low variance. So based on this criteria, the population-based search just emerged. So from the 6 previous candidates, these 3 algorithms made it through our criteria. Firstly, the particle swarm optimizer, because it has fastest climb and it's simple to configure. Secondly, the artificial bee colony. It has steadier gains on noisy Bitcoin test data. And thirdly, the hill climbing algorithm. We select it as our control group because it's ultra fast to test. It only has 1 parameter. I will introduce particle swarm optimization first. So here's an intuitive look at the particle swarm optimization. The blue dot here means the current position, and initially there's inertia, keeps it moving this way, and the personal influence pulls into the personal best, and the social influence pulls into the global best. And adding these 3 velocities together, here comes the new velocities, which pulls toward to the new position. And repeat this for 100 particles, and they collectively explore the profit landscape while sharing the discoveries. Next, the artificial bee colony. So here's how this works in our optimizer. We start from 50 random food sources for each employed bee, and in each cycle, the employed bee locally trick their own source, and then the onlooker bee watch the dance and copy the richest sites, refining them further. We store the best so far profit after every run, and if a source hasn't improved for 50 trials, its bee becomes a scout. The scout can abandon the stale source and creates a new branded one, which make it escapes the local optima. And we loop it for 100 cycles or until the clocks run out, and the colony's best nectar pot becomes our final parameter set. remarkably stable, around 60,000 in every pilot run. And thirdly, our control group hill climbing algorithm. We used a classic steepest ascent hill climbing algorithm as our baseline. So starting from random 14-dimensional vector, we trick one parameter at a time by plus or minus 0.1 to generate a single neighbor. And if the neighbor is better, we move to it and update the best solution if necessary. This method gives us a fast and consistent benchmark. However, it turned out that it tends to get stuck on the first local peak, usually around 35,000 to 40,000. So this control group makes it easy to see how much PSO or ABC can improve results through better exploration. Okay, so I will let Wenbo to introduce our section 4, the experiments and evaluations. Thank you.
Hi, thanks for each part. Let's now talk about our experimental setup and the evaluation strategy. We use historical daily Bitcoin price data from November 2014 to March 2022 to simulate a realistic training scenario. We split a dataset into two parts. Everything before January 1st, 2020 was used for training, and everything after was used for testing. This approach allowed us to optimize strategy parameters on historical data and then test their generalization ability on future unseen data, which is exactly what happens in real-world training. And our evaluation function is implemented as a Python function called evaluate. It takes 14-dimensional parameter vector, which is used to construct short-term and long-term moving averages. Those are weighted combinations of SMA, LMA, and EMA. The strategy then generates buy or sell signals based on crossover points between those moving averages. Then the simulated with fees will go through, and the final cash output will use as a fitness score. Then a full training simulation is executed, starting with $1,000, applying a 3% transaction fee on every trade. At the end of simulation, the final cash balance is returned as a fitness score, which our optimization algorithms aim to maximize. Now I'd like to focus on a key trade-off in our evaluation process. Let me give an example of use ABC algorithm. We tested it with 100 iterations and again with 1,000 iterations. As expected, the 1,000 iteration run produced a slightly better fitness score, but the improvement was marginal, just a few percentage points better than the 100 one. However, the running time increased by tenfold. A single run that previously took just 30 seconds now took over 15 minutes. This situation shows a law of diminishing returns in optimization. After a certain point, each additional evaluation offers minimal benefits, but adds significant time and cost to the process. So we decided to cap our experiments at reasonable values. For example, PSO with 100 particles. HCA is fast with 1,000 iterations. ABC is slow, so with only 100 iterations. This is allow us to strike a balance, completing experiments in a reasonable time frame while still having a meaningful representative results. Lastly, we ensure that all algorithms use the same evaluation function and training logic. All signal, phase model, boundary, and initial condition were kept consistent, so that differences in performance truly reflected the optimizers themselves, not differences in the way they were evaluated.
Thank you, Wenbo, for your detailed presentation on the experimental and evaluation strategy. Now I'll walk you through the performance summary of our three meta-heuristic algorithms: the particle swarm optimization, the artificial bee colony, and the hill climb algorithm evaluated on optimizing Bitcoin investment strategies. So this table shows the results averaged over 10 rounds. So let's get through it. The train average column shows how much profit the algorithm made on average during training. ABC leads here with around $67,000, followed closely by PSO, while the hill climb algorithm trails significantly. The train range tells us how much the results fluctuated across the different runs, and a large range like hill climb algorithm's $41,000 value means it's highly inconsistent, whereas particle swarm optimization with a range of only around $9,000 is far more stable. The train best and train worst gives the highest and lowest training profits. ABC scored the best at 78,000, but its worst was 59,000, and that's a major drop. Hill climb algorithm's worst, just for $36, raises reliability concerns. Moving to the test average, which is based on unseen data post 2020, particle swarm optimization and artificial bee colony both scored decently, with 2.5 thousand and 2.9 thousand, with hill climb algorithm again being behind. The test range and the test best and test worst follows the same story. ABC and PSO had the same test best at $5.5 thousand, but ABC dipped as low as $853, while PSO's worst stayed above $794. Finally, the time shows run time per round on average. HCA is super fast at under 3 seconds, but PSO and ABC took around 26 to 27 seconds due to more complex search dynamics. Now, if we look at the charts, the left one shows the training scores. It's evident that HCA consistently scores lower, while PSO and ABC have similar score ranges, though ABC tends to peak higher. The right chart focuses on the testing scores. Here, PSO stands out as the most stable, as its median line is closest to the X mark, which represents the midpoint between its best and worst performance. ABC shows the highest potential, but also the greatest spread, indicating instability. Moving on to the key takeaways. So, in summary, ABC has the highest ceiling, but is unstable. HCA is fast, but it's risky and very inconsistent. PSO is the most balanced for our method. It has strong scores, low volatility, and a decent speed. So this wraps up the comparison. Now I'll hand it over to Stefan, who will walk you through the conclusion phase. Thank you.
Thanks for that explanation of the results, Yusha. My name is Stefan, and I'll be going through some concluding statements. Population-based algorithms, such as particle swarm optimization, PSO, and artificial bee colony, ABC, have proven to be highly effective for optimizing trading robots, particularly when the problem space contains many continuous parameters. Not only did these algorithms generally make a large profit during training, but they also achieved higher final capital compared to the simpler single-state hill climbing algorithm, HCA. A key advantage was their ability to generalize better to unseen data, which is crucial in dynamic markets. Among the two, ABC stood out for its high average final capital on test data, while PSO followed closely behind by around $300. ABC seemed to have more instability in the training data with a larger range. However, this was due to the higher best value that it had. In contrast, the hill climbing algorithm consistently underperformed, highlighting the limitations of greedy local search strategies in complex multimodal search spaces. Based on these findings, we recommend using PSO or ABC when building robust, generalizable training strategies. These methods are better suited for complex tuning tasks than local search algorithms like HCA, which tend to get stuck in suboptimal regions. Looking forward, further improvements can include incorporating additional technical indicators, testing under multi-objective scenarios such as balancing return and risk, expanding the benchmark to include other meta-heuristics like genetic algorithms or differential evolution, and also to test these algorithms on a wider variety of assets beyond just Bitcoin. However, it's important to remember the real-world challenges of financial forecasting. Assets like Bitcoin are notoriously volatile, and their prices are influenced by sudden shifts, from geopolitical tensions to macroeconomic events, which are nearly impossible to model accurately. This means that while our strategies may perform well on historical training data, they often struggle on test data. This degradation highlights the inherent uncertainty in financial predictions and reinforces the importance of using robust adaptive algorithms. Designing models that can generalize well remains one of the key unsolved problems in this space. Finally, it's worth remembering the no free lunch theorem, in that no single algorithm is best for every problem. Each has its own strengths and weaknesses, and our review allowed us to make a meaningful comparison within this particular search space. Thank you for listening.